Okay, before I start, let me hand back the projects, okay? Maybe just come up here and get them. Loy Din, Jason Lee, Feng Nang, Michael Wu, Quan Cheng Lu, and Michael Lin. Here. Gerard Liang and Anatoly Smolkin. Ni Liu and Greg Gibling. If you know these people, you can take it to them. That might be good too. You know? Okay. Jack Chu and Toming Shi. Tamir Bakashev. Bagher Afshar and Sahand. Here, hand back. Wayne Wang. Wayne Wong, H-W-A-N-G. Whoops, missing. It's got separate here. Narachiman Liu, that should be what comes there. Jason Sarasathapat. Cindy Kwan, Beverly Wang. Okay. Whoops. It's just falling apart. Cindy Kwan. There you go. Archie Perlagos. Kevin Lin, Joyce Liang. Hand back. Jane Ju Sun and Grace So. David Mason. David Mason. Tan Ho and Tony Shi. Chen Chen and Mubarak. Chen Chen. There you go. Yeah. Kurt Moen. Jonathan Voelm. Anupama Bawander and Louis Alarcon. There you go. There you go. Matthew Leslie. Superman. No, who else? Matthew Leslie and Chuk Lo. Supermanium Katman. Phil Liu. Phil Chang. Lee Sun and Sandy Liu. Farzad Eskafi and Alfred Wang. Mong Ong, A-U-N-G. Win Toon. Henry Chen. David S. Lin and Michael Vo. You go straight back. Michael Liao, Ben Liu. Victoria Locke and Sue Lai. Okay, everybody get back? Okay, yeah. I saw that. What is it? Okay. Yours?
That's right.
This one?
Yeah.
Go ahead. Okay.
Oh, that's
Huh? Frank? Oh, no? I saw it. Frank Wong and...
Did someone take it already?
Who was it?
He's not here. I didn't see.
Did someone pick up Frank? Which was it? Frank what? Frank Wang and Gene Wong. I remember that. Narachman Liu, Narachman Liu, the spice part. We'll find it. I do remember. I'm almost certain. It might have just got caught in my. Okay. Well, I'll find it for you sometime. Maybe after class, or during break, let me look again. Okay. The way I graded the FO, so the way it was graded was this. If you missed some specifications, you got docked some points, like 5 points for each specification you missed. If you did a really bad job in the report, you lost a few points, but hardly anybody got that. And mostly it was on FOM. So the way the FOM was worked, it was basically I took the log of the FOM value. I should dig it out from my Excel sheet, but it's pretty weird. It's like, then I took this number, I subtracted off the lowest score, which was like 0.06 or something like that, so I normalized to 0, and then I normalized again to 25 over 27 or something like that. So basically it was a score 27. Basically it was a ramp from 0 to 25 of log of the FOM value.
Why did you go 27?
I normalized it back to 25. If I just taken this directly, it would have been 27, been the maximum score. So I normalized it back to 25. So maximum you could get for this. So then you start off with 70. Everybody started off with 75 points. You lost some points for specs, and you added points for the FOM value. So if you didn't lose any spec points and you got 25 points for the FOM, got 100 points. Okay. If you got low value for FOM and lost some spec points, you get below 75. I think the average was more like 85, 90, somewhere in there. Yeah. So, well, it's halfway through, right? So, okay. That makes sense. A lot of thinking went into this, as you can see. This was very difficult to figure out. Any questions?
Question. So, how big is your FOM in order to get 25 points?
Well, you couldn't figure it out, but basically, I think you had to be like greater than 5.2 gigahertz or something like that to get all 25 or something like that, because it rounded down. Then I rounded off. This is round, right? So I think if you're above 5 gigahertz, you're probably pretty close to get 25 points. If you're 2 gigahertz, I think it was 23 points or 22 points. The range actually was interesting, just to show you how big a range you can get in something like this. There's a range of 600 from the highest frequency response to the lowest frequency response, which is interesting, right? So I mean, so you get out there in the real world. I think what was interesting, range of 600.
Factor of 600.
Factor of 600, yeah, times 600, yeah, 600 times. So from the highest score to the lowest, highest bandwidth to the lowest bandwidth, okay? I think we tried to, said that, what is the rough best score you could get? And we talked about it, the figure, the gain bandwidth product being on the order of GM over CGS. And I think that came out with a number of around 7 gigahertz or something like that, or somewhere on that range. And the fact that people got 5 to 6 gigahertz shows that we're getting close to the kind of limit of the transistor for this circuit. So, kind of interesting. Okay. I think you did a pretty good job. I think clearly some of you didn't do so high on the score here. Didn't work as hard on it, obviously. And I think the biggie, and I've seen this before, was buffering into that last stage, right? If you didn't buffer into that last final output stage, try to drive it from a gain stage, you get hurt pretty badly there because you have a high output impedance of your last gain stage driving that big output stage, and so that was pretty damaging for your bandwidth. So you had to have a buffer in there of some sort. That's what most people did. Most people did lots of stages, 15 stages in some cases. I don't know what the maximum was, right? So lots of stages, followed by a buffer, followed by an output stage. I think it seemed like pretty much the common circuit. But I think all of you got all the specifications, so that was most important for me, that you got specifications and really, so I think you did a pretty good job on this project. That's good. I'm encouraged. I'm looking forward to the next one. So I know you're going to do just as well, if not better, right? Okay. I'm in sort of review mode now. Okay. Next lecture I'll put together one on this RF stuff, but I don't have that for today. What I was going to do is first, I was going to do a little first. Any questions on stability or feedback or any of that kind of stuff? I could do just some review things right now on that before I leave it. Any question about that? Anything you'd like me to do? Any problems I can redo again?
Can you do a 2-stage, like cascaded with feedback stuff?
Okay, sure. I can do a 2-stage with feedback. Let's just do one. Okay, so let's. Okay. What kind of feedback should we do? So let's take 2 stages. Okay. And let's put some feedback in this thing. Okay, so now how would we like to do the feedback? Okay, we have a choice. So let's take, this is V out, okay? And if we wanted to feed, we're going to want to do a series shunt or a shunt series? Okay, so shunt series. So shunt series means we're feeding back, what are we feeding back on shunt series? Current. So we're going to feed back a current. That probably means, so we need to come into this node right here, because even if we start off with a V in, okay, let's call this Rn, we're going to feed back into this node, okay? Series means we're sensing a current, okay? So how do we sense a current? Well, we don't connect right to V out. We've got to connect down. So if this is I out, is what we're going to be connecting, if we're connecting a current, and this will be I out down here. So we need to create something that we can sense I out with. So we usually put a resistor down here in this source lead right here. So we're not directly kicked out. So that means we're sensing a current. So the simplest connection would be, I guess we can do this. We'll just let me see here. So we can connect this back to here. Okay, so shunt, series, sensing. Now, is this positive feedback or negative feedback that I've connected up here if I only have 2 stages? I may have to put a 3rd stage in here. That's why I didn't fill that in. So how do we check that? Well, we go around the loop, okay? So let's kind of break the loop right here, and on this side, we'll put a positive increment of voltage, and we'll see what comes back here is a positive or negative increment, okay? Are we going positive direction or negative direction? Okay, so we send this up. That means if we just connect from here to here, that means this point, this is an inverter, right? So this means that this node's going to go down. If I directly connected to this point, that means this node will go down as well. And that means this node will go up. If this node goes up, okay, or actually I'm going down from here to here. If this goes up, then go down, sorry. This goes down. Then this node is going to go down. This node goes down. We come over to here through this. That means this is going down. So it's negative feedback. So I can connect these two up. Okay. Okay, series shunt, negative feedback. All right. Now, what we need to do, since we're feeding back, so here's I feedback right here, right? Here's I air. And we got this funny business here of this voltage input. We need to have a current input. So we got to redraw this input side here to reflect the fact that we have a real current input.
Can you do the second stage thing in the signal on that?
To what?
The second feedback.
Like the homework?
Well,
Let
it's like the homework, but it's not.
me do this one. Let me do this one. This is, I think this is.
Kind of like the other.
You already asked your question. Okay, so now I get to finish up here. Sorry. Okay. Okay, so let's take, this is the tricky part here. Let's take this input now and turn it into a current input, right? And this is a little bit tricky, okay? So I'm going to get rid of these two parts here. I'm going to redo this. Here's Rn, so I take this, and I do a Norton equivalent. And I'll take this, and so Norton equivalent of this is this circuit right here, right? And this is going to be Vn over Rn, okay? So this is exactly the equivalent circuit. I'm just driving it now from a current instead of from a voltage, okay? So let's forget about these two things right here now, okay? And here's what is a little bit troublesome, okay? This is, if I call this In, you know, where's I feedback? Well, I feedback's over here. Well, what about this resistor here? What's going on here? So I got another exactly equivalent circuit. What I'm trying to do is to get into the same exact form that I had, you know, when I first did these problems quite a while ago now, right? I mean, I have this differencing circuit going in, and this has all sorts of, you know, finite resistance associated with it and so on, okay? So I got to make this so there's a differencing node goes into all sort of finite stuff. So I have to move Rin so it's part of the basic amplifier or part of the feedback network. Doesn't really matter. I got to do one or the other. Let's make it this time. Let's make it part of the basic the feedback network. So in other words, the feedback network I will call as this. So this is the feedback network. So here's In, and I can redraw this. So here's, let me just redraw this. Here's In, and it's going to go into my basic amplifier like this, right? And here's my feedback network. Rn, and let's call this RF, okay? All right, and this goes over to here. This is shorted. So I'm redrawing the whole thing here, okay? So this goes over. Okay. I could even include, let's call this RS. I can even include that as part of the feedback network if I want to. I can call all of this stuff part of the feedback network. Okay, let's do that this time. I can include part of the basic amplifier, include part of the feedback network. It's not going to matter. Okay? So if this is all part of the feedback network, my feedback network looks basically like this, right? So let me redraw it. Okay, so the feedback network is RS, RF, Rn, and here's I out of the feedback network. And we short that, because we have to see how much current gets out of here. And this is going to be driven by I in of the feedback network, which equals I out. Okay? So what's F equal to? F is going to be equal to a current divider between RS and RF. Right? This is shorted here. We're trying to find this current here, so the Rn doesn't have any effect. Okay? So F is going to be simply equal to RS over RF plus RS. Right? So right now we got the answer pretty much. If I ask you what is, if T is much, probably likely, a couple of gain stages like this, T is going to be pretty large, right? So what's I in over, or I out over I in? It's going to be approximately equal to 1 over F, which is going to be equal to 1 plus RF over RS. Okay? Now, yep.
Did you use the current source because at INFB you made a current source for INFB, right? You see that?
INFB right here? Yeah, right.
Okay. Did you do that because it's a series?
Yes. The out. This is the input into my feedback network. I out.
So
Right.
if it was shunt, you would just attach a voltage.
That's exactly right. Exactly right. Okay. Now, what I want to do here. So, let's say I really wanted. You can just stop the problem right here. This is what's cool, powerful about all this stuff here, right? I in. If I want, what I really want to know is what V out over V in is. Right. So what is V out over in? V in. Well, V out, we can see here, is equal to I out minus I out times, let's call this RD1, let's call this RD2, times RD2. Okay? V in is equal to I in times Rn. So I can see that if I want to I out, so I could take V out over V in, which is really what I want, is going to be equal to minus I out over I in times RD2 over Rn. Here's I out over I in, plug into there, times RD2 over Rn, I've got V out over V in. Bang, all done, right? So that's pretty nice, right? I mean, that's kind of the power of this feedback network analysis. Once you get, know what kind of feedback it is, you can very quickly figure out, what the gain's going to be. This is a good test for your final answer, which you should be able to know. Okay, but let's go in and be a little more accurate about this thing. Let's get the basic amplifier with loading now. So let's calculate what the T prime is, right? And what we need to do now is go back to this circuit right here, and we use our technique. We say, okay, looking from the output here, this is shunt feedback on the input, what do I do with this output node of the feedback network in terms of the resistance looking into here? What do I do at this point? Short. Shunt equals short. So in other words, if I redraw this, I'm trying to find out, redraw this as basic amplifier with loading, it's going to be an RS times, that's shorted here, so it's going to be an RF to ground, okay? V out not really relevant to us, right? Because this is really an I out, what our circuit's all about here. Okay, and then let's see here. So we go to, this is grounded. Here is RD1. Here's RD2. On the input side. So looking into here, what do I do with the output? What do we assume about this point? open. It's looking into a current source, right? So that's an ideal current source driving it. So this is an open on this side here. So this would be an Rn and an Rf and an Rs to ground. And then this is In. So now what we need to do is to calculate what is the gain from I out over In. Okay, and what's that going to be? Well, to start with here, we'll have In times this. So what's the voltage on this node? Let's call this V1 or something like that. V1 is simply going to be In times Rn parallel with Rf plus Rs, okay, times, that gives us V1. This voltage here will be Gm times V1, okay, is times Rd1. So that's the voltage on this node minus that, okay. Now I need to calculate the current I out. What's I out going to be to? I out will be equal, let's call this V2, will be equal to Gm, let's call this transistor 2, transistor 1, will be Gm of transistor 2 times V2, which is just equal to this, right? Is that right? Is that anything else? Over what? Because the degenerated here, right? So it's 1 plus Gm2 times Rf in parallel with Rs. Okay? So that's the current out here. So the gain, so we can now plug all this stuff in. So what's the answer here, right? So V1 equals this, so I get V2 equals that. So I get Gm, there's Gm times V1, which is times In times Rn parallel with Rf plus Rs, okay, In times over, this is Gm, I should put Gm1 here, right? This is Gm1 times this Gm2 over 1 plus Gm2 times Rf in parallel with Rs equals I out. Is that right? Looks like I'm missing an RD somewhere. Gm1, oh, I missed the RD1 here. Okay. Let's check units. It's always good. Gm times R, unitless. Gm times R, unitless. 1 plus Gm times R, unitless. So looks like I got it. Yeah. Checking units is really a good idea. I mean, if you miss the units, you're off by 5 orders of magnitude. You know, real easily, right? Right. Check your units. This is a current ratio, right? I out over In, so that should have no units. If I was doing I out over Vn, then this thing ought to have units of transconductance. If I have V out over In, it should have units of resistance, right? So check your units on these things. That's always a good way to do it. So this gives us basically AI prime, that times the F that we calculated in this stage gives us our T prime. Then we can go in and calculate, you know, other stuff. Okay, we want to calculate. So looking into the input, what do we do? What's the input resistance? Rn of this thing is going to be equal to the resistance. This is the little Rn prime, right, which is Rn in parallel with Rf plus Rs divided by 1 plus T prime. Okay. All right. So that's, and Rn prime is just this in parallel with those two, right? So let's work with this for a second now. this now is the Rn of this circuit. But what is it the Rn of? It's the Rn of this circuit. It's looking into here. Okay? It's this Rn. All right? But probably what I wanted was this. Uh-oh. I got the same variables here. Sorry about that. Can I call this something different? I got two RNs. I got this RN and this RN the same. I want to call this RN hat. So this is Rn hat. Okay, this is the Rn of the whole circuit. Okay, this is Rn. Here's the resistor right here. So this, but I really want this one here, which is Rn double hat. All right, because it's not this Rn either. Here's what I calculate from this shunt series circuit. But I really want is the resistance looking into the other side of this Rn resistor that I have here. That's another resistor, another value resistance. So can someone tell me roughly what this Rn double hat's going to be equal to? What's the resistance at this node going to be? And what's Rn hat going to be? It's going to be Rn divided by 1 plus T prime. So what's that going to be? Small, right? If T prime's at all big, this is going to be a very small number, okay? So that means this resistance here is very small, okay? Looking into here, what are you going to see? Rn plus a really small resistance, because this feedback's making this node have a very low impedance. So looking into here, what are you going to see? You're just going to see Rn. It's going to be Rn plus whatever this thing's all about, right? Now, if you want to get really accurate about this, right, which is probably never really ever useful, okay, except in tests maybe, probably not even there. And certainly within 10%, we're totally home free, right? All T would have to be was greater than 10 to get this thing accurate within 10%, right? T is 100, we're accurate within 1% by just ignoring the resistance here. But what we really calculated is Rn prime is Rn. So let's now break this up again. Let's take this out of here and let's move it back again. So it's Rn in parallel with all of this stuff. So let me call that Rn hat prime. See what's going on here? That's probably hard to see. Let me redraw that part. I'll redraw this a second here. Here's our input. Here's Rn. Here we're going into our circuit with all this stuff in it, right? Here, let me redraw this now with RF, RS, and so on, right? This has all this business. Okay? So this is my R in bar, right? And that we decided is equal to little Rn prime over 1 plus T prime, right? That's equal to Rn plus whatever you want to call this looking into here. So what should I call that? Rn bar prime. Okay? So this is equal to Rn in parallel, rather, sorry, with Rn prime bar. See why I'm doing that? I'm trying to do that because if I can get this resistance here with Rn gone, right, that's the resistance looking into here with Rn gone. See? So if this is looking right into that transistor with all this stuff here. This is looking right into that transistor with all the feedback stuff. So what I'm trying to do is get rid of this Rn, which was I put in parallel, and it was series. So this is going to be equals Rn prime over 1 plus T prime, right? And what this just says is that, you know, you can work this out if you want. I mean, this equals Rn, which is a real resistor, times Rn prime over Rn plus Rn prime. If we know that Rn prime is small compared to Rn, because it's going to be, because it's divided by 1 plus T, right? We say that's small compared, and these two cancel out. So this is approximately equal to Rn prime. Right? So the resistance into here, it doesn't really matter that Rn's here, because it really is in parallel with something really small, basically. Right. So this resistance looking into here then will be Rn plus Rn prime, pretty much. Right. But this is really small compared to this, so it's pretty much just Rn. That's really complicated when I do this. It really is trivial in some sense, right? Maybe you can just kind of, all I'm doing is the fact that I calculate this resistance with this in parallel with everything else, and I got to get that thing out of the way. But it really all doesn't matter, because this is a really low impedance, right, at this point in time. So really, this effect of this Rn is really negligible. Yep.
That wasn't really my question.
Well, that was my answer. What's your question?
Well, I wanted to see what happened when you had like two feedbacks, or a couple of feedbacks connected with each other. That's why, like how the loading affected each one. That's why I wanted to ask.
Like the homework problem.
Well, yeah, but then I used different feedback types.
Yeah, I think like the homework problem where we had the. Let me just talk a little bit about the homework problem. I guess you get more on that from the TAs, but let's say we actually did. This had feedback inside feedback already, right? What is this? Where did this come from? I took a voltage here, right, and I calculated what I out was. This is really what kind of feedback? This little circuit right here. What kind of feedback is that? Any takers? Series? Series? Not really feedback? It's really a series shunt feedback. This is just a good old source follower, right? Right here. So this configuration here is series shunt. Okay, just a little part right inside here, right? Yeah. This I out isn't associated with that internal feedback, internal circuit.
Yeah, if you just look at the second stage, well, but you're not trying to detect at like the V out, right? You kind of like using the I out to feedback to the input, so it shouldn't be like series.
Actually, I guess you could do it. I guess that's right. I guess you could. If I call this I out, yeah, let's be series. If we calculate this as I out here, we could call this a series. I guess that's right. So this is a feedback network right here, just like you did in your homework where you had a shunt network. Okay, calculating. So basically, local feed. We could often have the case of, there's a series triple thing. It's in. I think I talked about this. It's in the notes, I think, right? So you can have a circuit like this, right? Okay, so this circuit, okay? There's local feedback and there's global feedback in this circuit, right? There's going to be local feedback associated with, as soon as we figure out the, looking into here, what do we have? We have a, basically degeneration going on here, right? And so we have to worry about is that, that, looking back into here, this is a series series circuit. So this is it's called a series triple, right? This is actually a pretty common circuit for very high wide band. If you want a lot of gain, in sort of one stage, you can build up something like this. And this is, well, I mean, in one block. Okay, right, I guess right, one block is one stage, 3 stages. Right? So looking into here, we see an open circuit, so we call this RF1, RF2, and RF3. It's RF3 in parallel with RF1 plus RF2. That's going to be down here in the source. So this is basically a feedback, a local feedback on this stage right here. We'll have local feedback on the input from the loading of this circuit right here. We'll have RF1 in parallel with RF2 plus RF3 in the source here. So that's local feedback in this input stage. So you can easily have a case of mixing local and global feedback. Your homework was a little weird because this source follower feedback we've worked out by hand many times. This series shunt thing, the shunt thing, we haven't worked out by hand so much.
So if you have something like that, would it be like 2 types of local feedback on the same transistor as well as a global feedback effect?
Yeah. Yep.
So anytime we have a source degeneration, kind of, it's local feedback, no matter if we're trying to do a common source or
yeah.
If we're,
Yeah. I think, what's this whole feedback thing all about? I mean, it almost maybe is complicated for you, but I went in and I took these single transistors and I started talking about, we broke them up and made it into a little local feedback network, right? It was probably more complicated to do it that way than it was to do what we did originally at the beginning of the year, where we just solved the answer, right? So with one transistor, it's almost not worth it to use all this machinery that we developed, okay? And so I think once you've got the answer for the single transistors, just use those answers. You don't need to sort of recalculate and use all that machinery, because there is some approximations being made in our feedback thing, right? Because of this business, we're not assuming that we assume there's no feedback going backwards through this circuit, and that can cause a little bit of error if the loop gain is low, right? And so if you only have one stage, you can begin to get low loop gains, and you'll get a little bit more error, right? And so when you have single stage, just treat it like a circuit. So I think the way to think about this is take these circuits, break the global feedback, put the, this circuit here, what we do is let me break it up. Okay, so I get rid of this, and I put this as RF2 plus RF1 here, and on this side it's RF2 plus RF3. So I get rid of that. Now I have these 2 circuits here. Now just calculate the input to output and forget about the fact this is feedback here. Just figure out the gain from this point to this point using the simplest way you possibly can do it. I mean, just, forget these are feedback problems. Now this is back to good old Ford amplifier gain problems and you don't need to do anything, you don't need to use the feedback analysis because it happens to be part of a global feedback problem, okay?
Don't we break it up like that anyway, and then we calculate the gain, and then we have to divide that by 1 plus t?
Yeah, I'm just saying when you calculate this part of the problem, don't get all confused about global feedback and local feedback. Just solve this problem. I mean, this is I out. Calculate I out over Vn. Just do it. Forget the fact that this had any global feedback around it at all. Right?
And is that the end result?
No, that gives you A prime, right? Yeah, right. And then you find, then there's an output resistance here. Then you go back to those other formulas with the global feedback stuff. But when you're doing this part of the problem, what was happening at homework, you kept thinking, well, geez, I have this global feedback, I have this local feedback, and which is which? Just solve this problem, right? Just do it. Forget about the fact there's any global. We've broken the global feedback. It's not a global feedback problem anymore. It's just 3 stages connected together with degeneration, right? That's a problem you know from a long time before. Okay. Any other questions? Yes. Why don't you use your mic? Why don't you use your mic? Yeah.
We were asked to move the 0 out
to infinity.
So when you look at the dot PZ statement, when you start looking at the dot LIS to look at the zeros, which are the ones, do you look at the ones on the right half plane only, the ones on the left? I'm a little confused about which ones actually make a difference after compensation, the zeros on which half plane.
Okay, so there only should be zeros in the right half plane, right? If there's any poles in the right half plane, that's problems, right? Okay, right, so only zeros. I think what the exercise in that project was all about was to, homework, is this, you increase that resistor, right? I mean, if we have this, is this problem here, right? Let me draw it, idealize, which what I analyzed in class, right? Or gave you the answer to in class. Was this circuit here, right? With this is RZ and this is C sub C. So for this circuit, okay, we found that, you know, the answer comes out to be C sub C times RZ, or 1 over G sub M of this transistor, let's call it transistor 2, minus R sub Z. So what I wanted you to do was look at SPICE, put in RZ, and watch this 0 move, okay? When it gets, so it's no longer, you know, there's a frequency associated with this distance right here, right? And it's kind of like 1 over, it's, you know, it's PZ, where, or omega PZ, right? That's the, the frequency of this 0, okay, in effect, right? And, which is equal to this, okay, omega PZ, okay? When this becomes much, much greater than any of the poles that we're interested in, okay, then it's kind of at infinity. Then it doesn't, then it's not important to us. What can happen, what does happen with this, it comes in back on the left half plane. Let's say our poles are sitting out here. Here's our omega P2 and so on, okay? This, it can get, and here's our omega P1, here's our compensation pole way down here. When this 0 starts to come back and get around the area of these omega P2 poles, then it gets interesting again. It's doing some more things for us, right? It's canceling out one of these poles over here, right? So you might say, well, geez, I could go in there and I could lay it on top of one of those poles and I can get rid of it. Yeah, you can actually, right? It actually will speed things up a bit. The problem with canceling of poles and zeros is you start changing the G, you use real transistors, and like your project's going to be, and you change VTs and you change some G sub M's, the pole can go in one direction and the 0 can go in the other direction, okay? There's no reason those poles and zeros have to move together once you line them up. And so you got everything lined up really nicely, you've meet all your stability criteria, but then you do a change of process, another process run, and that 0 goes in one direction, the pole goes in another direction, and all your little cancellation stuff just goes out the window. So this cancellation business is pretty, you know, it's generally not a good idea to try to rely on that very much. Okay, so that's bottom line. Okay. So 0 just means when it's sitting out here, far away from any of the poles of interest, okay, of infinity. Zeros in the left half plane are okay. Zeros in the right half plane are okay, as long as they're far enough out, right? As long as they're just not, you know, on the order. You know, this distance here needs to be, if it's on the order of that distance, then you've got something going on, right? This will begin to have contributions, right? You think about our pole 0 plots, right? I mean, if the, here's our compensation pole, and here's our second pole, and if we've got a 0 around that same point, it cancels out one of the poles. It's beginning to add phase shift, you know, and that's where the problem comes in. It's adding phase shift in the wrong direction. If it's sitting way out here, I guess once it gets to be more than 10 times the second pole, then it's not important anymore because there's no phase shift of it's beginning to have any effect, right? Okay. Yeah.
When you say 10 times, do you mean only the right half plane 0, or are you talking about any of the zeros, as in even the left half
Any of the zeros. I mean, the reason I say 10 times is, well, why do I say 10 times? Let's plot phase shift, right? So here's omega P here's omega compensation, here's omega P2, okay? So if I if my 0 is 10 times above this second pole, right? Right half plane, left half plane. The phase shift from that 0 doesn't start until that second pole, right? So it may go up plus 90 degrees, or it may go down minus 90 degrees. It's going to be 0 degrees at that second pole, and that's what I really care about, right? So just so long as the phase shift associated with that 0 is not becoming important, that you have to sort of deal with it, right?
So we should try to make all the zeros more than 10 times the second pole?
No, okay. Right half plane 0 adds phase shift in the bad direction for us, right? Left half plane 0s actually help us out. So you don't, what I said was you don't have to worry about it if it's 10 times. Now, if it's actually getting in there and actually adding some positive phase shift, canceling out some of the phase shift from some of your poles, you're actually helping phase margin. But maybe you didn't want any more help with your phase margin. Maybe your phase margin was already low enough, right? So I just think you have to begin to worry about it, begin to take care of it, begin to use it, okay? So, but it might be to your advantage. Might speed things up.
That's what we saw in
You saw your circuit there, yeah, right? That's fine. I mean, that's okay. But I mean, if you make phase margin, too good, that's bad too, right? Right. In this transient response, you'll see it. What will happen is you want to have that transient response. Okay, so let's talk about the project a little bit. What's the strategy to do those projects? Okay, the way you got to start off on those things is figure out your basic circuit. Okay, you got to drive a fairly low output resistance, so you're going to have to deal with the output stage. You're not going to be able, so it's going to be, my guess, something, and you don't want a lot of stages, as you know right now. So probably your second project is not going to be a good starting point. Probably more like your first project is a better starting point. Okay, and then what I would do is, of course, probably that first project is a lot of you cheated and really small currents, and so that's not gonna. You didn't cheat. That was fine. You could do it then, but just won't make it so useful now. You're going to plot your frequency response, plot the Bodie plots, okay, and find out what your stability issue is all about, right? Figure out how you make this thing stable. So go in. If you have a nice high gain stage, take your lowest pole, bring it to, compensate that amplifier, and then look and see, what your unity gain frequency is, okay? After you compensate it, okay, where T prime goes to 1. Then what you got to do is start going after those poles a little bit, okay, right? Start moving them out. You might, if you used really low currents in your first project, you might want to start that's probably not even going to be useful to look at that circuit, because the frequency response is going to be really bad, right? So start putting some more current through that thing so you get a little more reasonable current levels consistent with the power. You're given a power spec, right? So try to use all of that power. You don't want to. There's no advantage in saving because we gave you a hard spec on that. So use as much as you can. So up your currents, and so using most of that, the power that you have associated with that. Use what you have to do in the output stage and use everything else in the early stages. Okay, now, then you'll start looking at where those poles are, where that second pole is. Try to identify what they are and see what you can do to sort of move those out to higher frequency as much as you can. And there's some things you can change to help yourself out a little bit. Okay. After you've done that, this is all open loop now. Then close the loop. Put that circuit with the resistors in. And then start looking at the transient response. Do a pulse up and a pulse down, and start to look and see what this thing does. All right. You look at this region here, you find out the slew rate. You look at this thing wiggle out here, and that tells you what your small signal settling response is. Okay. The tight relationship, if you're using a Miller-like op-amp, the relationship between what you're limiting is in the slew rate versus this small signal settling thing is. Be aware of that. Then do what you can to sort of, I'd say a good balanced design is to have the slew rate time comparable to your small signal settling time. Okay? That's kind of a reasonable way to do it. If you make one 10 times the other, you've probably put too much current, or it's usually a trade-off between these two things. Making one better makes the other worse. You're probably a better trade-off is to kind of have them two comparable. Okay. The other thing you need to worry about is the long-term settling of this thing. Remember that, as I said before, that's set by where this thing finally comes to is 1 over f times t prime over 1 plus t prime. Well, 1 over f is that ratio of resistors, right? So we'll assume that's very accurate. The area that you'll get will be this t prime over 1 plus t prime. You'll have to have t prime large enough so that the area you get from this, we call this the static settling, okay, is small, because that's going to add in. If we blow this up here, this thing is kind of, let me just draw that. So here's, this thing's finally settling out. Okay, let's say you have a fairly low phase margin. But let's say the final answer, what it should be is, let me just draw it as a red here, is this. Okay? And let's say the plus or minus 1% is, so here's plus 1%, and this is, or 0.1%, whatever it is, and minus 0.1%, okay? If your final, oh no, I'm sorry, this is not right. I mean, what I want to do is like this. This is plus 0.1%, and this would be minus 0.1%. Relative to this is the exact value we'd like to have. So you can sort of trade off a little bit here. As if you have your loop gain relatively low, your static error is going to be fairly large, and this thing's going to have to really settle out before it finally comes to the right, before it finally stays inside this bound right here. Okay. If you have more loop gain, okay, so let's say you have more loop gain. Let's say you have a lot of loop gain, so your static settling is very close to it finally ends up at this point. Then plus or minus 0.1% will be here and here, right? And you can sort of see that it's going to be way back here that you're going to finally get inside the plus or minus 0.1% band. So there's a trade-off between increasing the loop gain to reduce your static settling and the small signal settling, which will, as you have more gain, of course, that makes it harder to make the amplifier have a higher bandwidth. Okay, get that? So in other words, I mean, what happens is this thing is going to come up, slew rate period, settling period, and then final static settling. So this thing here is set by the A0F. This is set by A0F times 1 over F. So this gives you your error due to static settling way out here. There's this small signal settling stuff, and there's a slew rate time. Right? So then after so get the thing set with the open loop case, figure out what you want to do for your static settling, how much gain you're going to have in that open loop.
Why would you not want as big gain as possible for the loop gain? Because then you have like almost zero error.
So let's make the loop gain really big, million. How are you going to do that?
How are you going to do that?
So let's say I want to have a loop gain of 1 million. What's your amplifier going to look like? Lots of stages. And what's wrong with that? Lots of stages mean a lot of poles. A lot of poles mean difficult to compensate, right? As you have more state, it's the old gain bandwidth product thing. Just hitting you again, right? This corner, this T thing, where this thing goes to 1, where that T goes to 1, is kind of that gain bandwidth product number. That's kind of where you're. That's the. So as you ask for more gain, you're going to have less bandwidth. Bottom line. All right. Think about it. Here's another way to look at it is this. Here's two cases, right? A0, case 1. Here's T equal to 1. This is gain of 1. Okay. Here's our compensation pole, right? If I increase this gain, okay, what do I have to do? I've got to move this pole further and further back, right? So that makes the compensation more difficult to do, basically. So you get away with the lowest gain you have, but so there's trade-off now between static settling, slew rate, small signal settling, and we're going to give you two. Okay, so here's something else about it. I think we're giving you two different SPICE files. Now, how do you deal with that? A really important part of the problem is to figure out what's the worst case. This is another part of design that's really difficult. A lot you have to think about. So there's one's going to be slower. One's going to have a larger VT, okay, and a larger K and a smaller K prime. So that'll be the slow file, okay. The one that has as VT goes up and K prime goes down, that slows down the circuit, the transistors, okay. So it's going to be more difficult with that process to get higher bandwidth, okay. The other one where VT is small, so this will be a VT small and K prime goes up. This is the fast, right? Fast process, okay? So you're going to get more gain with this, okay? And you're going to have to worry then about stability problems. So what you have to deal with is, this gives you more gain, this gives you a lower pole, okay? All right? So you have to figure out worst case condition between these two extremes when you figure out how do you compensate this, okay? So you're going to have to look at both of these, and you'll get a good feeling now for, the dependence of process on
Which circuit is the FOM?
worst. The worst case. We'll do for both of them. We'll see what the worst case is. Okay? Probably it will be from the slow run, the slow thing. You'll have to compensate to make sure it works for the fast case, but that'll make the slow case even slower, right? All right. Now, how's the real world like? We're giving you two files. You know how it really is? In the real world, they usually give you there's three groups of the parameters. They group them to three, and typically what you do is you can do is you have these three groups, like VT might be in one group, K prime might be in another group, and some other process numbers, capacitances will be in the third group. It's not like that, but they'll be divided up. So you can get the typical process group. You can get the fast group. You can get the slow group. Of course, there's the old slow, typical, fast group, right? Or the fast, typical, slow group, right? Right? You got to figure out the worst case condition between all these 9 possibilities, right? Now, in actual fact, you usually work with the slow, typical, and fast groups, right? Typical is something in between the slow and the fast. You can create your own typical one if you want to. How might you do that? Just take the average value of the VTs and the average value of the K primes, or some sort of mean of those two, right? To figure out your own intermediate value when you do your design, right? Because if you do everything with the slow, then you look at the fast, you're going to be way off. You do everything with the fast and do everything slow, you're going to be way off. So if you kind of start with your design sort of intermediate between those fast and slow processes, it might give you something that's a little closer to, optimized answers you're going to get. Then you can put in the fast and slow runs later on and start doing those. So, anything else? This project's pretty realistic. I mean, you're getting, you're using real process files. Real runs. So I think it's if you get out and do a job and someone asks you to do a design, you'd be something not that different from what you're doing right here, right? So you're getting pretty close. So. Any questions? Other question about that? 10 minutes. Let me just talk a little bit about how you might use one of these circuits. Let me talk about A to D converters. Okay, this is typical. Right? What's the world really like? The world is like a bunch of analog signals. There's stuff coming, RF signals coming into your cell phone. There's speakers you have to drive. There's, inside your DVD player, there's some amplifiers that are coming off your laser detector there, right? Okay, so what you need to do very often with these circuits is sort of there's the real world, okay? And this is quite often what you will do as you go out into your jobs. If you're working in this mixed signal area, which is kind of what they call the stuff we're designing now. There's the real world. You go through some kind of signal conditioning. You know, amplifiers, or maybe the transducer you have is really a current output or something like that, or maybe it's coming off an antenna. You need to amplify it for a while or condition it in some way. Get it up to some reasonable value. And often these amplifiers are variable gain. Okay. You often need to filter it. You want to do is to get rid of, this is frequency response, right? Maybe get rid of high frequency stuff because it's not going to be very interesting to you. Okay. Because the final stage of all these things is often an A to D converter. Okay. And then you go into the digital processing, which will make real small, right? That's right. What the digital guys would do, they'd sort of show our stuff as a little teeny thing, and they show the big digital part, right? Well, we can show their stuff, little teeny thing on the edge here. We don't care about it. But there's going to be a lot of stuff happening over here, right? And our job is to get from the real world into this digital world with the lowest power, the lowest cost of circuits that we can, and working over the widest range. And another thing is using the cheapest process. That's what often happened in the old days, is still happens now, is there's lazy designers, not people that took 140, right? People who would say, okay, I don't want to try to figure out how to do this in CMOS. I want to use, you know, some process that really helps me, like a nice bipolar process, has some really good transistors. And in fact, even now there's, you know, you can buy CMOS is a process that has bipolar devices inside a CMOS process. So it's kind of a compromise. But the problem is this, you add these extra steps, that makes this process cost 20 to 30% more. And that's just deadly. You know, if your thing costs 20 to 30% more than someone else, you're just not going to sell anything, right? I mean, typically when you make your final chip, the question is, what can you sell it for to these people out here? They're going to put the DVD player together or make the cell phone, whatever it is. You're lucky if you can sell it for 40% more. That's the margin you call about. The margin over what your cost is from what they're going to buy it for. If someone else, if you use a process that's 20 to 30% more, that means your margin's down to 5 to 10%, right? Compared to someone else. And you can't sell it for more because people are going to buy it from the other person. So what's that 5%, 10% have to do? It has to pay your salary. And that's not very much left because it's got to pay your salary, it's got to pay the marketing guy's salary, the president of the company who's making all sorts of money, right? And so, right. So you want to make sure there's lots of money left over to pay your salary as much as you can, right? And the best way to do that is to use a cheap process. So you don't do this by CMOS stuff. You figure out how to do it in CMOS, okay, right? And the most simplest, straightforward process. Okay, so that means we got to do all this stuff in CMOS. So the question is, how do you do it? Well, amplifiers we've been sort of talking about in this class. And this is what we've been doing here. I mean, you might think about how might we change the gain of things. Okay, we could talk a little bit about that. But pretty much the circuits you've been doing so far have been, you know, about amplifiers. The next two big classes of circuits that are really important are filtering and A to D conversion. The question is, how do you do those things? And fortunately, they're built around the basic block that we have. This op-amp is often the critical part of these circuits. Okay, so let me just talk about a little bit of a beginning of this A to D converter process to show you the basic technique that we use. There's another little circuit sitting inside here. It's called the sample and hold, and it's just a simple circuit, but it's important, and it uses some of the techniques that we'll use for filtering and other part of the A to D. So let me talk about the sample and hold. What's the sample and hold all about? Let's say you have this is the signal coming in. So this is your input signal. Okay? Maybe it's the RF signal from your cell phone after it's been amplified up. In a cell phone, I'll tell you what you have to do there. That signal has to be amplified up like 1,000,000 times. I mean, it comes off your antenna at microvolt levels. We got to get up to like hundreds of millivolt or volt levels at best, right? So you got a huge amount of gain, and usually it's some amplification, filtering, a whole bunch of stages of it. So let's say we finally get it up, and our signal's up on the order of, tenths to volts up to a volt, let's say. So a nice big juicy signal. What we need to do is convert this in to digital bits. So what do you need to do? To convert to digital bits, you don't want to work with this continuous time signal. This is time in this direction. You want to convert this to sampled and held signal. You want to sample this signal and hold it for the sample time of the A to D converter, the conversion time of the A to D converter. From 120, those of you taken that, right? If you have a signal which has a bandwidth of, let's take a cell phone. Typical cell phone bandwidths are, say 100 kilohertz or something like that, right? 100 kilohertz. How fast, megahertz. Let's take megahertz, okay? That's the RF signal, but we filter it and we mix it down to lower frequencies. So it's really the bandwidth of signal of interest is only megahertz. Let's say it's a megahertz signal bandwidth. How fast do you have to sample it in order to be able to faithfully get all the information out of that 1 megahertz bandwidth? Right? Who knows that answer? How much? 2 megahertz, right? You got to sample it times 2 times that rate. And that will then you can fully reproduce that signal. That's the Nyquist sampling theorem, 120. So we should take 120, right? So what that means is we need to sample at 2 megahertz. So that means every 0.5 microseconds, we need to take a sample. Well, we hold that sample after we take it. After another half microsecond, we take another sample and hold that. Take another sample, we hold that. Because during this hold period, that's when we're going to do the A to D conversion. We're going to take this voltage and try to convert it into 0110 corresponding to that voltage level. Okay? What kind of circuit would you do to sample the signal and hold it? So there's a question for you. Okay? Well, let me show you one that's what typically people do. Okay? Let me show you two. Let me show you a really easy one, then I'll show you one that works. Okay, right? Here is our input signal. It's varying like all this. And then I put an MOS switch, okay, in series with that input. And I put a clock on this. So this is and this goes from 0 to the supply, 1.2 volts. So I'm clocking the gate of this transistor. And let's have it go into a capacitor. And we call this the sampling capacitor. Okay. And then what we could do is have this go into an op-amp that buffers it and takes the output here. So how does this work? The way this thing works is we take, if this signal here, let's say this signal's at, let's say this switch actually goes between minus 0.6 volts and plus 0.6 volts. And let's say this signal's around 0 volts, and this is right in the center here is 0 volts, so it goes plus and minus around 0. But this switch here is swinging plus and minus 6. So let's say this is typically 0 volts. You can see when this is at plus 0.6 volts, this voltage right here will drive through this transistor, and this voltage here will be also at 0 volts. So this transistor goes into what region? What region of operation will this transistor be in? If this is 0 volts and this is nearly 0 volts, we got a voltage on the gate here, it's 0.6 volts here. Linear. So this guy goes into linear region. VDS is very small, and we have a big VGS on it. So this guy goes in linear region. So this circuit degenerates in something like a resistor and a capacitor. And the signal here, while this is high, will be tracking that signal. So this signal here will be the same as this with this RC time constant. But if this transistor is like a picofarad and this resistor is like a megohm times a picofarad is a megohm, kilo ohm, let's say, 1 kilo ohm. you can easily make a switch have a kilo ohm on resistance. That's 1 over GM, right? So that'd be what 1 over RC, which would be like 10 to the 9th. So it's like a 10 to the 9th radians per second. So it's huge bandwidth. So you usually have very fast bandwidths here, right? So this thing tracks this voltage very well. And then what we do is we turn this switch off. What happens when this switch turns off? Goes to minus 0.6 volts. What does this transistor do? What region to go into? Cuts off. Becomes an open circuit. So that signal is held on this capacitor. So we can model this transistor as something like this. It's like a switch that goes on and off and drives this capacitor. So when it closes, it drives this switch. When it opens, it holds the value on this switch. So you begin to see what we do in this kind of thing. A switch and capacitors are really the core of a lot of stuff we're going to do to these filters and these A to D converters. Well, what we'll do is take amplifiers, put switches and capacitors around it, and do all sorts of funny things with our signals, okay? Filters, A to D converters, D to A converters, all sorts of stuff, okay? So I'll show you some of that next time, and I'll also start the RF design stuff.